Good evening, students. In today's video we'll be discussing the handle properties of textiles. Handle properties of textiles are crucial because they help in assessment of the feel or the touch of the fabric. It is of course important to determine how does the fabric feel on initial touch on the skin, whether it is rough, it is smooth. So these kind of feelings or sensations are basically subjective in nature, but there are some methods which can be used for objective evaluation of these properties. So in today's video we'll see that what are those objective methods for determination of these handle related or the tactile related properties. So these evaluation methods will help in determining the draping property of the textiles, stiffness or the limpness of the fabric, its luster, smoothness or roughness. So the objective evaluation of fabric handle involves determination of crease recovery, bending length and drapeability. So all of these three are related to the handle properties or the handle characteristics of the textile materials. So the first property that we'll be discussing is crease recovery. So basically what is crease recovery? It is the ability of fabric to resist the creasing. In normal day-to-day use, particularly if we see cotton garments made from cotton fabrics, they are subjected to maximum creasing when they are washed or even during wear, during use. So how well a fabric can resist this creasing is determined by the property known as crease recovery, and it will depend on fiber type, of course. Like some of the fibers, wool, silk, they exhibit good resistance to creasing, that is they have the ability to recover back from that creased position, while there are still some other fabric types which are made from material fibers like cotton, viscose, linen, which show poor crease resistance. So when the fabric is creased, what are the mechanisms involved? How does this creasing occur? So basically the resulting deformation has two components. What are those two components? Displacement of fibers and yarns relative to one another. The fibers and yarns can get displaced relative to one another, or the fibers can get stretched on the outside of the curve. So the importance of these two mechanisms depend on the radius of curvature that the fabric is bent to, that which of these, whether the deformation occurs because of displacement of fibers or because of stretching of fibers, will depend on the radius of curvature to which the fabric is being bent. At smaller radius of curvature, the fiber gets stretched rather than displacement between the fibers and the yarns. And the unaided recovery of fabric. Unaided means when no mechanical force is applied or when the fabric is not subjected to washing. So at that time, how does it recover from this creasing? It will depend on the elastic recovery of the fibers. That is, what is the stored elastic energy and whether that stored elastic energy is sufficient to overcome the friction that resists the movement of yarns and fibers. So it is the interplay between these two forces which causes the fabric to recover from the creased position. Crease recovery at lower curvatures is governed by frictional effects associated with fiber movements. However, at higher curvature, it is governed by the elastic response or the stored elastic energy in the fibers. Internal friction of the fabric depends on the structural factors such as the tightness of the weave. So this is constructional parameter which affects the internal friction. So if we have to see the mechanism of crease formation, basically how the crease formation takes place. So in the textile structure, we know that there is crystalline and the amorphous region. So when we take the example of cotton fabric, when cotton fabric is subjected to washing or when it is exposed to water, so what actually happens in this internal structure? The cotton fiber will readily absorb the moisture. Cotton fiber will readily absorb the moisture owing to its hydrophilic character, and because of the absorbed moisture, Because of the absorbed moisture, the internal structure gets affected. The absorbed moisture facilitates internal polymer chain movement in the amorphous fiber areas by lubrication, as can be seen in this diagram, that as the water molecules get absorbed, so there is some repositioning of the bonds taking place in these locations. As can be seen, hydroxyl groups are formed uh, in the amorphous region of the structure. So it affects the hydrogen bonding between these adjacent polymer chains. So between these adjacent polymer chains, the hydrogen bonding is taking place, and until some external force, mechanical force, or is subjected to these fabrics, so these bonds will remain as such. That means the crease will be maintained as such until and unless some mechanical force is applied to break these bonds. So when a moisture-laden cellulosic fiber is stressed, the internal polymer chains of the amorphous area are free to move to release that stress. When some external mechanical force is applied, for example, when that fabric is pressed, so you are applying mechanical force, heat and pressure. So in that case, these bonds can get reformed, they can get broken to release the stress which is being exerted because of the external force. So the hydrogen bonds can reform between the polymer chains in their shifted position, in effect locking in the new configuration. So a newly formed wrinkle or a crease will remain in the fabric until adequate moisture and mechanical force are applied to overcome the internal forces. So until and unless some external force is applied, these polymeric chains will remain in this newly formed position where they have been forming bonds between the adjacent polymeric chains. So when mechanical force is applied or when the fabric is again subjected to water, only then this reformation or rearrangement of bonds will take place, because the structure needs to release the stress which is being caused by the external force. And until and unless the external force is applied, they will remain in this position, because of which the creasing takes place. A newly formed wrinkle or crease will remain in the fabric until adequate moisture and mechanical force are applied to overcome the internal forces. Therefore, the breakage of hydrogen bonds in the crystalline region, the breakage of hydrogen bonds and the formation of new hydrogen bonds in the amorphous region causes the crease formation. Because of these bonds that are forming between the adjacent groups in the polymeric chains in the amorphous region, this causes the crease formation to take place. So one method by which this formation of crease can be prevented is of course by application of finishes on these fabrics. So there are different crease resistant durable press kind of finishes, basically where cross-linking agents are applied. So what is the purpose of these cross-linking agents? These will be helping to act as cross-link between the adjacent cellulosic chains, as we just saw in the amorphous region, that the molecules were free to form bonds between the adjacent polymeric chains. But if the cross-linking agents are introduced in the structure, the cross-linking agents will restrict this formation of bonds between the chains of amorphous region. The swelling of cellulosic fiber by moisture can be reduced by the application of self-cross-linking agents that mainly cross-link with cellulose molecules. As a result, the swelling of cellulosic fiber by absorption of water molecules can be avoided in such a case, and this is the purpose of using such durable press finishes to make the fabric crease resistant. Even in case of cotton, it can be made more crease resistant, or recovery to creasing can be increased by the introduction of such cross-linking agents or by application of surface finishes on such fabrics. So then comes the evaluation or the determination of crease recovery. How this property is tested? Crease recovery test involves folding the specimen in two and placing under load for a given length of time to form a crease. So basically the test sample, it is folded in half, and it is placed under a load for for a specified period of time. Generally it is kept under known load for 5 minutes, and then it is allowed to recover for further length of time, and finally the crease recovery angle is measured. So the crease recovery angle is measured on an instrument called Shirley crease recovery tester. So this is showing the schematics of the crease recovery tester. So Shirley Crease Recovery Tester consists of a circular dial of this kind. It consists of a clamp in which the specimen or the test sample will be mounted, and this is how the specimen will be hanging down. This is the knife edge along which the specimen needs to be vertically aligned. That is, the limb of the sample should be vertical in this position, and this circular dial has graduations where the crease recovery angle can be measured. So here the sample size that is used is 40 mm into 15 mm, and 20 samples are tested. We need to test separately for warp and weft direction when we talk about woven fabrics. So the test sample, when it is folded, the ends are held by tweezers, and then it is put under a specified amount of load. Generally 10 newtons of load is used to pressurize that fabric, and it is kept under that load for a duration of 5 minutes. So half the specimens are folded face to face and the other half are back to back. Then after the application of load for 5 minutes, the sample is immediately transferred to the holder of the measuring instrument. So the sample is transferred onto this clamp, and uh, it is positioned here in such a way that it reaches the it reaches the backmost position of this clamp. One leg of specimen is inserted as far as the back stop. The instrument is adjusted continuously to keep the free limb of the specimen vertical. So this free limb of the specimen is kept vertical, and the time is given to recover the sample. So here we are giving time for the for applying pressure, which is 5 minutes, and another 5 minutes when it will be recovering from that crease that has been formed during the loading. So instrument is adjusted continuously to keep the free limb of specimen vertical. Crease recovery angle is measured by reading the scale when the free limb is vertical after 5 minutes of the removal of the load. So when the sample was mounted here, so its vertical limb, this free lying portion was made vertical with reference to this knife edge, and the crease recovery angle can be read from this uh, circular dial. So the next property that we will be discussing is related to the bending properties of the textile. So in this test, basically the bending length, the overhanging length of the fabric, the bending rigidity, and the bending modulus can be determined. So here basically this instrument is based on cantilever. So this instrument is based on the cantilever principle of testing. So here the horizontal strip of fabric is clamped at one end, and the rest of the strip is allowed to hang like a cantilever under its own weight. So this is the platform on which the fabric will be resting. This green portion is showing the fabric. It has a graduated scale which is usually marked in centimeters and on the other side. So like when the sample along with the scale will be moved from the unsupported portion, the fabric will start bending, and it bends under its own weight. So basically in the determination of bending length, we are interested to know that how the fabric is bending when it is unsupported. Here from this position it is unsupported, so how much does it bend? So generally the reference line is given, and for this instrument, as the tip of the fabric will reach this line, it will be making an angle of 41.5 degrees, and at this position we measure the overhanging length of the fabric, that how much of the fabric has reached that point. So from that the bending length is determined in this instrument. So we can obtain a bending length, the bending modulus, overhanging length using the same instrument, and this is basically showing the Pierce equation. The Pierce equation helps in coining these relationships between the bending length, the overhanging length, and the bending modulus, where G is representing the flexural rigidity, M is the weight of the fabric. So the bending length or the bending property of the textile is dependent on the fabric weight or the areal density. L here is giving the overhanging length. Overhanging length is representing this length of the fabric, which when unsupported will be hanging, will be bending under its own weight. So mind you, this overhanging length is different from the bending length, because this overhanging length is used for the determination of bending length. So as you can see, this L and C, they are different. C is representing the bending length, which will give a measure of how stiff a fabric is, what is its flexural rigidity, and this L parameter is giving us the overhanging length when the fabric is mounted on that instrument, and how does it hang or bend under its own weight. So the bending rigidity depends on the fabric mass per unit area or the fabric weight, which is M here, and L is representing the length of the projected fabric or the overhanging length. And using this equation, the bending length can be determined for any type of textile material that we wish to. So from equation 1, which is this one is the equation 1, Pierce coined the term bending length C, which is the length of rectangular strip of material which will bend under its own mass to an angle of 7.1 degrees. So this is an empirical equation, but the instrument does not measure it at an angle of 7.1 degree. When angle of 7.1 degree means that this theta value is 7.1. So if we equate it using this value of 7.1 value of theta here, so that becomes C equal, that becomes 1, and C is equal to L. So bending length, if it is equal to the overhanging length, that is if this length becomes equal to the bending length, so that is not possible, because that means the fabric is very limpy, it gets bent to a very large extent. So usually in this instrument, this is the angle theta which I was referring to from here, from this line, from this horizontal line to this inclined line. So this angle is kept at 41.5 degree for this instrument, and as the tip of the fabric will meet this imaginary line, so that length will be measured, and that length is considered as L, the fabric length projecting or the overhanging length, which is then used for the calculation of this bending length. So this is an ideal condition which is actually not possible, that is when theta is 7.1 degree. So when theta is 7.1 degree, it will be a very small angle, and this fabric will be exactly very close to this inclined line. So in practical situations, this angle theta is not 7.1, which was given by Pierce equation, but it is kept somewhere around 41.5 degrees. And when this tip of the fabric will be meeting this line, so that time the bending length can be determined. So bending length depends on the fabric weight, and it is an important component of drape of fabric when it is hanging under its own weight. So bending property of the material will also influence the draping behavior of the material, which we will also discuss in detail when we discuss the drapability or the drape properties of textiles. Greater the rigidity of the material, the greater will be the draping coefficient, and such a material will show less drapable properties. So this is how flexural rigidity is a measure of fabric stiffness. So flexural rigidity, as I told, G is indicating the flexural rigidity here, which can be determined when the tip of the specimen reaches a plane inclined at 41.5 degree below the horizontal. So this is the horizontal plane, and this is the inclined plane, which is kept at an angle of 41.5 degree below the horizontal, the overhanging length is twice the bending length. So we need to make this correction while measuring the bending length, that is the L will be twice that of C. So we need to make this correction when we are determining it at an angle of 41.5 degrees. So this shows the schematics or the image of Shirley Stiffness tester. This instrument measures the bending stiffness of fabric. This instrument measures the bending stiffness of fabric by allowing a narrow strip of fabric to bend to a fixed angle under its own weight. So this is a fixed scale. The fabric will be made to will be supported till this position, and then it will be made to hang under its own weight in this inclined position. The length of the fabric required to bend this angle is measured, and from this length the bending length can be determined. The test sample which is taken here is 200 mm by 25 mm, and higher the bending length, the stiffer will be the fabric, its stiffness will be higher. So if we have to define what is flexural rigidity and bending modulus, flexural rigidity is the ratio of the small change in bending moment per unit width of the material to the corresponding small change in curvature. So G is giving the flexural rigidity, and it can be determined if the value of bending length is known to us. The value of bending length can be determined from L, from the equation we just saw. So here flexural rigidity is dependent on the fabric weight, the areal density of the fabric. So higher the areal density or the weight of the fabric, the higher will be the flexural rigidity. And the bending length and flexural rigidity are also, as can be seen from this equation, are directly related. That is, higher the bending length, higher will be the flexural rigidity, and such a fabric will be more stiff. Bending modulus, the stiffness of the fabric in The stiffness of the fabric in bending is dependent on thickness. The thicker the fabric, the stiffer if all other factors remain the same, if all other constructional parameters are kept same, and if only the thickness of two samples vary. So the fabric with higher thickness will show higher stiffness and higher bending modulus, because it is a property that is dependent on the fabric thickness. So the bending modulus is independent of dimensions of the strips. It is not affected by the dimensions of the strip. However, it depends on the material thickness. It is tested so that by analogy with solid materials, it is a measure of intrinsic stiffness of that material. So the bending modulus is given by 12 into G into 10 raised to power 3 divided by third power of T, where T is the fabric thickness. G is representing the flexural rigidity here. So this method, which is based on cantilever method of testing, is basically suited for woven fabrics. But for fabrics which are too limpy, or like in case of knitted fabrics, this test method is not very suitable, and for knitted fabrics a different approach is used for determination of their stiffness. So this we will be discussing in the next lecture, that how the bending rigidity and the bending length or the bending properties for knitted materials are determined basically by three methods: the ring, pier and the heart loop method, which will be the part of the next lecture. So this is all for today. Thank you.